So in video 3, what we want to look at is the effect of multiplying either the sine function or the cosine function by a scalar, a positive or negative real number, with the exception that we won't let a equal 0. So first what we want to do is recall what the graphs of the sine and the cosine function look like. So our toolbox function, f of theta equals cosine of theta. Our toolbox function was a function that started at a high point, dropped to a low point, and went back to a high point. And the cosine function went from a high point of 1 to a low point of -1. And what we want to remember is that we were graphing the x-coordinates as we rotated through an angle theta around the unit circle. So there's a couple of key ideas that we want to look at for the toolbox function before we look at multiplying the toolbox function by the scalar a. So two key ideas. We have amplitude and midline. So the midline of a trigonometric function, cosine or sine, is just the halfway point between the highest point on the graph and the lowest point on the graph. So if I take the high point and I add to it the lowest point, and I take the average of those two numbers, I get the equation of the midline. So in this case, the midline is actually going to be the theta axis, where we have x equaling 0. So the theta axis is the midline, the line that is halfway between the lowest point and the highest point on the function. So that's the idea of midline in trigonometry. And the idea of amplitude is simple. It is just the distance or the height that the function gets above its midline. So in this case, because we're going from -1 to 1, the highest we ever get above or below the midline is a height of 1. So in this case, for the toolbox function, we say the amplitude is 1 and the midline is x equals 0, the coordinate x equal 0. So then what we want to do is think about, well, what is going to be the impact of multiplying the toolbox function by some scalar a? And what we want to recall is from pre-calculus 1 that this is just a function transformation. This is going to be either a stretch or a compression. If the number a is greater than, so actually if the number a, the absolute value of a, is bigger than 1, then we're going to get a stretch. And if the absolute value of a is less than 1, we're going to get a compression of the function. We don't have any horizontal or vertical shifts in terms of function transformation, so a is just going to stretch or compress our toolbox function by a factor of a. And then what we want to remember from pre-calc 1 is that if a is less than 0, if it's negative, if a is negative, we're going to reflect our function in the horizontal axis. So we're going to reflect in the theta axis. So it's really straightforward. When we're graphing a times the cosine, all you need to do, we'll start off with no tick marks. All you need to do, if you're going to multiply the toolbox function times a, which is just going to cause a stretch or a compression, just draw what the cosine function would usually look like. The cosine function, the toolbox function, looks like this. Well, it should look how I draw it if I were a good drawer. I'm going to draw it in pieces, so if I have to erase something, it just erases a piece. So draw what the cosine function looks like. It starts from a high point, it goes to a low point, and then what we want to recognize is if we're multiplying by a, this is just going to go from a to negative a instead of -1 to 1. In other words, the range of the cosine function, x was an element of the interval from -1 to 1, these are the outputs. And the effect of multiplying a times the cosine, you're really just multiplying this interval, this output interval, by a. So if we distribute this into the interval, we get x as an element of the interval from negative a to positive a. And this is the graph of the cosine function. It's still going to go out to 360 degrees or 2 pi radians. It's still going to break into the 4 key intervals: 90 degrees, 180 degrees, 270 degrees, just like it did before. All a does is stretch or compress. So if we are then looking at the sine function, the game is going to play out the same way. If we do a times the sine function, then draw what the sine function normally looks like. The sine function starts at 0, goes to a high point, comes back down to the theta axis, goes to its lowest point, and then returns to where it started. And for the sine function, we know that we're plotting the y coordinates on the unit circle, and this is the theta axis. This is our angle of rotation in standard form, and it's going to go to 360 degrees or 2 pi radians, and it's going to break into the 4 key pieces where we have 90 degrees, 180 degrees, 270 degrees, and 360 degrees or 2 pi radians. And then recognize that a is just going to cause a stretch or a compression. So we're going to go, instead of from negative 1 to 1, we're going to go from negative a to a, because the sine function, just like the cosine function, has a range where the outputs go from negative 1 to 1, and all that's going to happen is we're taking the sine function, which goes from negative 1 to 1, and we're multiplying it by a, which means it's really a times the interval of the toolbox function, so it's going to go from negative a to a. So let's do a concrete example. Let's graph 4 times the cosine function. So again, the idea is don't put any tick marks in before you graph. If you're hand graphing, draw what the picture needs to look like, then label the key features. So this is the cosine function, so I probably don't want a y there. I'll either put f of theta here or I'll put x here, driving home the fact that the outputs are x coordinates on the unit circle. It's a non-standard labeling, but I think it makes sense. And this is the theta axis. And the cosine function, we know it starts high, goes down to its midline, the theta axis, drops to its lowest point, comes back to the theta axis, and then returns to where it began. And because we're multiplying by 4, instead of the outputs being on the interval from negative 1 to 1 like they are for the toolbox function cosine of theta, we're going to be multiplying that interval by 4. So we're going to go from negative 4 to positive 4. So the high point on the graph, I'll now label it. I'll label my lowest point on the graph as negative 4. I know that this goes all the way out to 360 degrees or 2 pi radians. The graph breaks into its 4 key features: the high point, the low points, and the theta axis intercepts. I know this is at 90 degrees, or pi over 2 radians, 2 pi over 2 radians, 3 pi over 2 radians, 4 pi over 2 radians, which reduces to 2 pi, and 2 pi over 2 radians reduces to pi. So there's my tick marks, and there's the graph of my function. We'll do one more example before we call it a wrap. So now we're going to graph f of theta equals negative 1/2 sine theta. So again, this time y would be an appropriate label because these are the y coordinates, or label this axis with its function name f of theta, and we know this is the theta axis. So the sine function, think about what the toolbox function looks like. The toolbox function sine theta usually starts at the origin, goes up to its high point, down to its low point, back down to the theta axis, then down to its lowest point, back up to the theta axis, which is where it all began, and then it repeats itself over and over again. But the negative sign on the scalar is going to cause a reflection in the theta axis. So what we want to recognize is that this graph will be reflected over the theta axis. So when we draw it, we don't draw the sine function, we draw the reflection of the sine function in the theta axis. So I'm going to start at the origin. I'm going to go to my low point, because usually I'd be going to my high point, but I've been reflected, back to the theta axis, up to a high point, back down to the theta axis. And only after you draw the function do you put your labeling in. Here I have a 1/2, the negative 1/2. The absolute value is a half, so the amplitude, the distance between the high point and the midline, or the theta axis, is going to be a distance of 1/2. The toolbox function goes from -1 to 1, so now my new function f of theta is going to go from 1/2 times that interval, which is -1/2 to 1/2. So I draw in the high point. The high point is now at a half instead of 1, because all of the outputs have been multiplied by 1/2. It's going to go to a low point of -1/2. The period is still 2 pi, or 360 degrees. So I break my graph up into the 4 key points: the high point, the theta intercept, the low point, the theta intercept, and I label in my degrees. So I can do this either in degrees or in radians. 90, 180, 270, 360, multiples of 90 degrees, and there is the graph of my function.